Now we want to look at some applications of nuclear chemistry, and we're going to start with half-life.
So to make sure we're on the same page, what we're interested in is this idea of nuclear stability. We know that nuclei can have a certain number of protons, a certain number of neutrons, but there are only a small number of possible combinations that lead to stable nuclei. When we say stable nuclei, it means that don't fall spontaneously, just fall apart. And there's a lot of, everything has to be just right. Nucleus can't be too big, it can't have too many neutrons, and it can't have too many protons. So everything has to be balanced just right. We get that nice band of stability. When most nuclei that aren't those black dots, those combinations of protons and neutrons exist, they would be unstable. And so we would say that they would undergo some sort of decay, some sort of process where they will undergo, their nucleus will change, resulting in a more stable nucleus. And there's all sorts of different ways for these different nuclei to decay. We learned about the 5 different types of nuclear decay: alpha and beta decay, gamma emission, positron emission, and electron capture. And each of these different processes corresponds to different changes to the nucleus, right? Alpha decay, you're losing mass. That's when a nucleus is too big. Beta decay, an electron is lost, right? That's negative charge leaving the nucleus, leaving it with more positive charge. So do you have not enough protons? Are there too many neutrons in the nucleus? Well, kick out some negative charge. Now there's more positive charge, more protons in the nucleus. Gamma emission is the nucleus just too energetic, lose some of that energy as gamma emission, but not any sort of mass or proton changes. Then positron emission and electron capture either lose positive or gain negative charge, in both cases decreasing the amount of positive charge in the nucleus, turning some of those protons into neutrons. So these different types of decay that exist correspond to answering the different questions. Why is a nucleus unstable? Is it too big? Are there too many neutrons? Are there too many protons? So we have these different ways that a nucleus decays, but not all unstable nuclei necessarily decay at the same rate. Okay? And so there's a rate at which they decay, going back to our good friend kinetics. And so the more unstable a nucleus is, the faster it'll decay, the faster we would predict that it will fall apart. And so at the same time, if we talk about a stable nucleus, so for example, helium-4. Helium-4 is a stable nucleus. We would predict that it does not undergo decay. What that means is that basically over the length of time of the universe, so for our, tens, billions of years, those helium nuclei that were around, that are existing since the beginning of the universe are still here, right? They haven't decayed over that time frame. So over, say, 1 trillion years, they may decay, but over 10 billion years, they're not going to decay. And so half-life is then the amount of time that it takes for 1/2 of a substance to undergo radioactive decay. We talked about half-life in the kinetics chapter. It still means the same thing, the idea of the amount of time it takes for 1/2 of a substance to undergo a chemical reaction. In this case, we're just specifying radioactive decay. And so, say we are dealing with, say, some sort of parent, we have some sort of nuclear process. And so at 0 half-lives, we have some number of the red nuclei, right? They're red, they're the parent. And then after 1 half-life, some of them have undergone decay. And we know that when a nucleus undergoes decay, it turns into a different type of nucleus, right? It has a new name, and that's distinguished in the second photo with the green circles, right? So we started with, we have some number of parents, and then after 1 half-life, half of those parent nuclei have become the daughter product. Then you'll note after the second half-life, it's not that the other half is gone, but instead, half of the red nuclei at the 1 half-life time mark have now been converted into the daughter product after the 2 half-lives. So when we're thinking about this half-life time, so the first half-life, we lose 1/2. So half of these become green. Then in moving from doing the first to the second half-life, half of what is still red now becomes green after that second half-life. So you'll note there's still some red present. So one of the things to note, after 2 half-lives, you're not done. You instead, it's a multiplication factor, not a subtraction. So you multiply by 1/2, then again, you multiply by 1/2. So if we look at some different nuclei, some different nuclides that we have, all sorts of different things, we can see that they all are characterized by different half-lives. So we have some things that have a half-life, this phosphorus 28 is 0.28 seconds, and it does positron emission 0.28 seconds. That's extremely fast, or quite fast. So this phosphorus 28, we would say is pretty unstable, right? This is going to be pretty highly radioactive. After about a minute, basically everything is gone. And if you had, say, like, a gram of it, that's a ton of radiation that has come out. And so it's really, really reactive. All of those nuclei are going to be emitting a ton of radiation, a ton of particles are coming out of that. We could then get to things that are on the order of years, say 28 years, thousands of years for carbon, or say 4 billion years for uranium-238. We will note uranium-238 is still an unstable nucleus. We know that it does decay. If you have uranium nuclei, we know that they will be emitting alpha particles, right? They're real big. 92 is greater than 83, so we're expecting they'd be too big. They're going to emit alpha particles, and they will do it. They just aren't that active. So if you have a sample of uranium nuclei, most of them aren't undergoing decay, or they just take a long time for them to decay. Whereas these really short half-life things, the halves a second ones, those ones are just flying, right? Almost all those atoms, all those nuclei are falling apart really, really quickly. And so if we return to this graph idea that we've looked at of the band of stability, again, number of protons on the bottom, number of neutrons on the top, we can now color code based off the length of a half-life. So the black line corresponds to stable nuclei. And then we can see that red is relatively stable, right? Those half-lives are 350 years to 46 billion years, so really long half-lives. And then the yellow, the green, and the blue on out. And so those blue ones are less than half a second. And so we can see that this half-life, the size of a half-life, allows us to characterize just how relatively stable a nucleus is. So that band of stability, those black lines, those black dots, those are the nuclei that are actually stable. They do not decay. We can see that around that band of stability, there's mostly red and yellow dots corresponding to half-lives of 12 days and longer, right? So those are things that would potentially exist for, a relatively long time. So something that has a half-life of 1 million years, if you have a sample of that, after a day, barely any of the nuclei have actually decayed, right? There's still a lot of radiation coming out, but there's still a lot there. So that sample would still be present. It will decay over long time frames. And one of the reasons why we use that number of, billions of years is the idea of, the nuclei of those atoms that existed, say, at the beginning of the universe, are they still all here? And if you have something where the half-life is, on the order of millions or billions of years, they're not all here, right? Millions of years, they're mostly all gone. But billions of years, that's a number of half-lives that have already passed. And so some of that will be gone, and anything that existed from the jump. But you can see that as you get really far from the band of stability, those black dots, you get the blue, those are less than a second. Those are just functionally, useless. Or like way out here, you'll note the really big nuclei that are, really, really big, over 100 protons. Those are just going to fall apart very, very quickly. And so we can also see that, half-life, longer half-lives mean relatively, not only are they're less radioactive, so they're safer, right? They're not generally emitting a ton of radiation. Really short half-lives are dangerous. Okay, so when we want to use this half-life, we can rely on the fact that all nuclear decay processes are first order, right? If you remember, first order just means, if we think back on mechanisms, that there's just one molecule. Or one object that's undergoing the reaction. And nuclei are just by themselves. They're not interacting with any other nuclei. And so nuclear decay is always first order. So half-lives of first order do not depend on initial concentration. The equation for half-life is the logarithm of 2 divided by the rate constant. Natural log of 2 divided by the rate constant, so whatever the rate constant is. Because it's first order, we can also come up with the integrated rate law. So traditionally we use, for integrated rate laws, the concentration of A for over time. When you're dealing with nuclear processes, usually we use this N term. It means the same thing. You'll note we basically just replace that capital N with the brackets A. Because you're dealing with nuclei, they're generally not dissolved in solution. And they are instead just a raw count. So this N, capital N, means amount of nuclei present. That could be measured in mass or just raw total number of nuclei. You started with 1 million nuclei, you now have 750,000 or something like that. So if we want to use the half-life, these sorts of ideas, those integrated rate laws allow us to predict amounts of objects, or amounts of, in this case, nuclei, that are present over a certain amount of time. And so we can plot out what that would look like. If we look at something, for example, iodine-131 has a half-life of 8 days. So every 8 days, another half of the material decays. But the important thing to note is that what it means for what that actual raw amount is of 1/2 changes based on whatever the starting amount was, right? If you start with 10 grams for that first half-life, going down by half is 10 divided by 2, you have 5 left. Now, to do the second half-life, again at 16 days, you can see you again go down by half. Because you started at 5, going down by half brings you down only by 2.5. Again, half brings you down, half brings you down. You're decreasing by 1/2 of whatever, a factor of 1/2 every time, not necessarily that you go 10, 5, 0. Okay. So when our integrated rate laws, we've used those in general, we can in many different ways. A lot of times when we're working with nuclear reactions, because they are always first order, and because we really characterize them based on a half-life as opposed to a rate constant, a lot of times we rearrange the integrated rate law into this equation, which has the exact same information, but it's based around half-life explicitly for a first order process. And there's no rate constant that's in there as a K. Generally because half-lives are a bit easier to measure, and they're usually used in the context of nuclear processes. So our variables here, T is still the elapsed time, T with the 1/2 is still the half-life, N naught right here is going to be the amount of nuclei that we start with, and this would be the amount of nuclei after or at time T, where again that T is the same as that T at the top of that fraction. And kind of one of the ideas here is we know that at each half-life we lose 1/2 of the amount. So T divided by T 1/2 that's your total time divided by the length of a half-life, which corresponds to the number of half-lives that have elapsed, right? 1, 2, 3 half-lives, and so you multiply 1/2 to that power. However many times, every time you do a half-life, you lose another 0.5, another factor of 0.5. Okay, so let's see it in use. The half-life of mercury-197 is 65 hours. If you begin with 45.6 grams of mercury-197, how much will remain after 195 hours? Okay. So when we're solving a problem, we always want to start by thinking, what do we want? How much will remain? That we're talking about an amount of mercury-197 remaining. Mercury-197 tells us that this is, we're dealing with some sort of nuclear, probably some sort of nuclear process. We've got a specific nuclide that's specified here, and we're dealing with amount. We can think about where is it going, right? Could be a kinetic process there. This is a kinetic question that we're looking at, but because there's a nuclide specified, this is nuclear decay that we're looking at, and so we probably want to use our half-life equation. And so we want that NT, right? How much will remain after a certain amount of time? That's always a sign that we want the NT. If ever we were asked what the initial amount was or how much did we start with, that's where we want the N0. So we want NT in this case. So do we have the other variables? So the other variables we would need would be N0, T, and the T 1/2. Okay, so N0 is going to be the initial amount that we start with. Well, we are told that we begin with 45.6 grams. So if you begin, if you start with, those are the kind of words we're looking at for our N0, looking for when we're talking about N0. For time, then T time, we can see that we're given 2. We have 65 hours and 195 hours. Because we're told this T without the subscript 1/2, that's going to be a general time specific to this particular isotope or particular setup, sorry. So we're dealing with 195 hours. T 1/2 then, that is a half-life. And we're told here that the half-life of mercury-197 is 65 hours. But in general, one of the other things we can do, you can look it up. You can Google mercury 197 half-life and find out that it's 65 hours. So that 65 hours, you can always look up what that information is, and that would be whenever that's available. So you're not always going to be told explicitly the half-life is 65 hours or 10 days or 1,000,000 years or 20 seconds, whatever it is. You would need to potentially look that up on your own. All right, so let's actually solve this. I got nt is equal to n naught, and then the 0.5 is raised to that t over t1/2 power. And so I'm just going to plug in those variables. N naught was the 45.6, the t was 195 hours, and the t1/2 is 65 hours. One of the things you'll note right here, those time units need to cancel out. In this case, both of our values were given in hours, so it works out. But say you were told it's 195 hours, but the half-life is given in like minutes, you'd have to convert one of those into the other. So you will need to, a lot of times you do need to do unit conversions. But we can evaluate that. 195 divided by 65 is 3. So what this means is that after 195 hours, 3 half-lives have elapsed, right? We started, each one was 65 hours. We hit a 195 hour, so we've done 3 times through a half-life. So that 1/2, or 0.5 to the 3rd power, is 0.125. That's 1/8. And so that gives us that left is 5.7 grams. Okay, so after 3 half-lives, you've lost a pretty sizable chunk of what you started with. And so we can start to see that a half-life mercury 197, 65 hours. That's what, ballpark 2 days and change, just short of 3 days. That's a relatively short time for radioactivity. So this sample after 195 hours, so that's 7 days, you now have quite a bit of radiation that's come out of this thing. Right? All of that means a bunch of energy has left because a lot of your mercury 197 has undergone decay and turned into something else. So it's not that it left the material, right? You still have mass, a pile of mass, but only 5.7 grams is left as mercury 197.
Participation 421, question 1. The half-life of cobalt-60 is 70.9 days. How much of a 50-gram sample of cobalt-60 is left after 1 year? This is the first question on participation 421 due Tuesday, April 21st at 11:59 p.m. over on Blackboard. The link to the assignment is right below the document where these videos are posted. Again, the half-life of cobalt-60 is 70.9 days. How much of a 50-gram sample of cobalt-60 is left after 1 year? Okay, got our first question for participation 421. Only one more video left in the set. Not many videos there, kind of on the long side, but only one video left. Looking for any more participation questions. See you there.